So, welcome back to particle physics and the Standard Model. This is lecture 24. So, in the previous lecture we saw how to successfully embed a massive spin 1 particle with 3 degrees of freedom into a field theory without compromising on the field into which you are embedding this being a 4 vector, a Lorentz 4 vector, right. And we saw that you could have yet another Lorentz invariant term that you could add, and then from the equation of motion by manipulating it we found that there is 1 degree of freedom that you can completely remove. It happens to be the correct degree of freedom because the constraint itself is Lorentz invariant, and so you have removed an unwanted Lorentz invariant spin 0 component. Okay, that is exactly the degree of freedom you have removed by taking the reducible representation of the Lorentz group. 4 vectors are reducible representations of the Lorentz group, they break down into 3 plus 1 and you remove the 1, right. And when we wrote down the Lagrangian, we made use of the Maxwell tensor or the field strength tensor notation and ended up with writing the equations of motion, which are also known as the Proca equation in this case. And we saw a nice feature of doing this, which is that under a redundancy in the field description, if you were to take the a mu field to some other vector field as a mu plus a 4 derivative of any function of x alpha of x, you find that the field strength tensor is left invariant, right. So, that gives us confidence in using gauge invariant theories, which we will do as we go on. Okay. Okay, good. Now, it is instructive to write down how the solution looks like for this equation of motion, for the Proca equation of motion. Okay. So, how would it look like? Once again we make a mode expansion. Remember we did this for the Klein-Gordon field, that is what we are going to do here also. Okay. I have an integral of all the momenta in the problem, and now this A is my operator which takes care of destruction or creation and so on. Okay. So, I am just going to write, it is not the most general solution, I am going to write a solution where it carries just the destruction operator. Okay. So, I have written down this as a quantum operator, but where is the Lorentz index? That does not sit on A, okay, because that is still an operator. So, that index I am going to give to the polarization, okay. And of course, this is a propagating degree of freedom. So, I have an e power IPX, alright. What is I? I basically takes care of the component index, okay, of the polarization vectors, okay. So, in other words, the epsilon mu's, they form a set of basis vectors here. Okay. So, that means mu is component index for the A field, okay, literally A mu, right. And I is the component index for the basis vectors. So we just saw we had 3 degrees of freedom, right. So there are, so you can form a basis using that. Okay. And again, remember we had this as the polarization condition, and I am including an I now, right. This is how we define polarization, right. That did not come, I mean we just did not pull it out of the air, it actually came from the Lorentz condition, the Lorentz gauge condition. Okay. We enforced this actually, right. The Lorentz gauge condition literally translates to a condition on how you contract momenta with polarizations, and that is what, you know, the basis vector is what ultimately we tend to call polarization. So it is all working out, right. All the earlier intuition we had about spin 1 particles is working out in the field theory, right. Okay, very good. And finally, just so you do not think that the Prokha-Lagrangian is some theoretical curiosity, this is exactly the Lagrangian that describes the Z boson, the W bosons, the rho meson, and so on and so forth. All the massive spin 1 particles that you can think of, this is how you do it, okay. This is how you do the embedding, and this is what we use for calculations. Okay, excellent. Now I think we have all the tools to construct a Lagrangian for massless spin 1 states. Okay. Alright, so what are, how many degrees of freedom do we have now? So this is what we started out with, right. So of course we have 2 degrees of freedom, and we saw that the polarizations now can be written, again I am writing linear polarizations, you are always welcome to write circular polarization vectors also, different bases, right. Okay. Here is a little curiosity. Remember that I can now write the 4 momentum this way. I have to, right, because energy, there is no mass involved, the energy is the momentum, right, and I have chosen the z direction to be the propagation direction, correct. Now would not that mean that if I want to satisfy this condition, right, I also have, I am just going to call it f, we will see why in a second. This satisfies the condition, right. So why do not I write this? This f stands for forward, it is called the forward polarization for obvious reasons, it is not a longitudinal one, it is a forward one in this case, right, because you have it in the z direction also. Why can't I write this? The reason is that there is another condition, right, the normalization condition. What is the normalization condition? You want this to be -1, right, but is it -1? No, this is manifestly 0, correct, and that tells me that this is not a physical polarization, this is not physical. Okay. Okay. there is yet another way to see that this is unphysical. Okay? And that is to make use of the gauge invariance that we mentioned in the previous lecture, right. So, do you agree that at this point I can now write down the Lagrangian without the mass term, I just set the mass to 0 here, right. So, I am just going to get for a free theory, this is my Lagrangian, that is it. Agreed? Okay. And I know that this Lagrangian, unlike the Proca Lagrangian, this entire Lagrangian is invariant under gauge transformations, right. This particular gauge transformation will leave my Lagrangian invariant. Agreed? Remember that in the Proca Lagrangian the m square term was not 0, so it was the Lagrangian itself was not gauge invariant, only the f mu nu was gauge invariant. But since I am explicitly constructing the Lagrangian using two gauge invariant quantities, of course the entire Lagrangian is also gauge invariant, right. Okay. So, what happens now is that since the forward polarization is proportional to p mu, right, they are exactly the same except for normalization, right. So, since the forward polarization is proportional to p mu, what I have is that I can always pick a mu as a derivative, right. Why? Because a mu is after all written in the basis of e mu's, right, and that means if a polarization is proportional to the momentum, what is the momentum? The momentum after all comes from a derivative, a 4 derivative, correct. I can always write a mu as some 4 derivative of a scalar field for some phi, in which case look at this condition, okay. That means if I choose that alpha, right, equal to minus phi, something weird happens, right. These two terms cancel each other now. Agreed? So, that means I have gone into some field configuration where this whole thing is actually 0. Isn't that strange, right? Let me write that in words. This would lead to a configuration of fields where if I call this whole thing a mu now, right, I can call it a prime mu if you want, right. A field configuration where the whole a mu is 0. Okay. So, isn't that strange? Because that means the theory exists still, okay, but the field does not actually, right. In other words, we are now in a pure gauge theory, that is the gauge exists, the gauge corresponds, when I say gauge I mean this alpha of x, the alpha of x is there, okay, I can still make those field redundancies, but then I can always go to one particular configuration which is this, because I have complete freedom in choosing alpha, where alpha is there, it has a value, but the field has gone, the field has disappeared. So, it is a pure gauge theory, a pure gauge because alpha is the gauge, but there is no a mu, okay. So, of course, a pure gauge theory cannot be a physical theory. I need a field to embed my degrees of freedom in, I want that field to transform like a 4 vector, okay. Okay, good. So I am mentioning all this because this is the kind of language that one should get used in field theory. Okay, these are the consistency checks that we need to do to see whether our field theory description actually describes the particle physics that we want. Okay, excellent. Now here is another observation. Once again, even for the massless field, right, if this is the Lagrangian, once again vertices like these are forbidden trivially, right. We saw this for massive spin 1 fields, now we see this for massless also, because I have only two A mu fields to marry each other basically. Okay, good. Okay, excellent. Now, what is the equation of motion for this? This is nothing but Maxwell's equations. Agreed? This is exactly what we are describing now with covariant tensors. Okay. Let that be the case, we can still write down the equation of motion in terms of the fields that we wrote down. So I am going to write the equation of motion, which looks like this. Okay. Now it is a bit instructive to expand this in terms of the components, and I can now write this down as two different equations. Here is one, and here is one more involving another combination of spatial and time components. Okay. Okay. Excellent. Now, do we have a problem? Yes, we do, because once again we have taken a theory, right, with 4 components, and now we want to embed 2 degrees of freedom, and in the equation of motion I still have the 4 components, correct? So what should we do now? Well, the first thing you want to do is to still eliminate 1 degree of freedom. So eliminate 1 degree of freedom with the Lorentz condition, right, the Lorentz gauge condition. It is not really a gauge, although the name has stuck. It is just the condition that you get from the equation of motion itself by taking the derivative, which is what? This. So this we know how to do, this we saw already. Okay. But what about the other one actually? There is one more condition, right? So what do I do about that? This is where a very cunning trick has been devised to embed particle physics into field theory. Okay. And the trick is, remember that you have freedom in your gauge, right? You can pick alpha x to be whatever you want, correct? So the trick then is to fix the gauge. That is why I am writing this in capital letters. This is a very, very important trick to make field theory and particle physics talk to each other. Okay. when you do that, would you agree that if I were to work in only one gauge, I do not have the freedom anymore to, I mean, to start with I have the freedom to move my alpha x wherever I want, but if I were to go to one particular gauge and then write down the Lagrangian equation of motion only for that gauge, would you agree that one more degree of freedom in A will get eliminated? Of course it will, correct? So that is what we are going to do, and I am not going to go through the algebra of this because it gets very counterintuitive and confusing. So rather I am going to ask you to look at the exact argument in Schwartz's QFT book or in any number of QFT books. Okay, it is a very standard trick. You can even look this up in Wikipedia, but I am just going to write the gauge condition here. Okay, and a popular gauge that people use to get this trick done, okay, is the Coulomb gauge. The Coulomb gauge is nothing but this. Okay. You might have seen this again in when you learnt electromagnetism. Even in electromagnetism we saw gauge redundancies, etc., right? And then even then in certain situations we picked the Coulomb gauge, agreed? Of course we can write that in the 4 vector notation as well. So this is the gauge in which we are going to write down our equation of motion. Okay. How exactly this corresponds to removing one of the degrees of freedom, this you can go check in Schwartz, but intuitively you can already see, right. Even if I just fix a gauge in the spatial derivatives, in the spatial part of the problem, it will still work out. Okay, good. So what would that make the equations of motion? That would mean I just have this, okay. That is my propagating modes, and then of course if I write that I have to write the other conditions that I imposed. This is the Coulomb gauge. What else? We had the Lorentz gauge condition also, right? That is the Lorentz gauge condition. See, that is the trick now. Consistently, by making use of the gauge redundancies that were given to us in the Lagrangian, we have fixed or we have eliminated the unwanted degree of freedom that we did not want in the first place. Okay? And this is borne out when you write down the solution as well. So what is the general solution? You can write down here. I can always write the A mu in terms of basis vectors again, right, e power I px. So actually, yeah, there is an I and then I can sum over the I for the basis vectors just like before. Agreed? Good. And then of course when I apply the equation of motion, I will get p square equals 0 from the equation of motion, which is good because we know that photons are massless, and I will just write this in 3 vector notation for each of the polarization vectors. Remember, I labels the polarization vectors, not the components of the vector, right. This I get simply from the gauge choice, right, from the Coulomb gauge itself. Right. And I get one more thing actually, I also get epsilon naught equal to 0 from the gauge choice. Okay, pick these 2 gauges, you will find epsilon naught is also equal to 0, right. So all of this is working out, right. Remember in the forward polarization we saw that when you had epsilon naught not equal to 0, here you had some unphysical degree of freedom, right. So that is not happening already, all of this is consistent, good. And of course the epsilon 1 and epsilon 2 will fall out of the equation of motion, these 2, okay. And indeed just for completeness sake I am going to write that you can always change the basis for this and go to the circular basis where you have a right circularly polarized wave, which I can write this way, because remember these can be complex, and a left circularly polarized component that goes like this, right, easy peasy, right, good. That is excellent. To round this up, to round up our discussion of spin 1, let me say one more thing as a consistency check about this epsilon naught. Okay. See, I told you that epsilon naught ultimately came, this epsilon naught being equal to 0 came as a gauge choice, right, came from a gauge choice, right. So in particular the Coulomb gauge added along with Lorentz gauge. With just the Lorentz gauge you are not going to get this, but if you also impose the Coulomb gauge you are going to get this condition on the time component, right. So if this condition is not imposed, by the Coulomb gauge, right, I can consider a polarization vector like this, right, generically, right. Okay. This is sometimes called, I am not sure what it is called, I think it is just called a time polarization, okay, temporal polarization if I am remembering it correctly. Nevertheless, notice that there is already some problems with this, right. In the first place I cannot normalize this, right, I am not able to normalize this using the usual condition, right. This is what I wanted, but I do not get this, correct. But that is not all, this is a time like vector, agreed, and we know that time like vectors are unphysical, right. So, by imposing the Coulomb gauge, I have also avoided introducing these unphysical degrees of freedom that could have potentially been in the problem. Okay. Very good. So, we have wrapped up spin 0 and spin 1. Now, we know how to embed correct degrees of freedom into field theories consistently. Then now next we can move on to spin half fields, which we will do in the next lecture. Embedding fermions into spin half quantum fields is its own challenge, and we will see how to tackle that. Dirac tackled it first very successfully, and we will see how to interpret that, and we will see how to rewrite the entire Lorentz group itself, okay, on the way there. Alright, thank you. See you in the next lecture.